Okay, so this is the second part of the recording. And this is the part that gets a little bit simpler. Um, this is the part that not simpler. That's not rightly the right word. This is the part where we get um uh into actual sockets. This will make a little bit more straightforward sense because we're actually going to be programming here. We're going to get to talk about sockets. We're going to talk about sockets concept, including IPC. We're going to explain socket creation, including domains, types, protocol, and addresses. Sockets are becoming one of the more common mechanisms for interprocedural uh, communication, just simply because it's one of the more flexible ones. Even on the same machine, we'll talk about socket creation, including, oh yeah, we said that already. We'll discuss socket functions, including send and receive, close, and its relationship to I/O. It's actually quite simple if you let it be. Send and receive are read and write, if you think about it from that perspective. It's not horribly complicated. We're going to primarily be creating TCP sockets instead of uh, UDP sockets. Um, so, I mean, we'll talk about both, but we won't. We'll do one primarily. And then we'll discuss client server opera. We'll talk about binding sockets to addresses, right? So we need a server to actually stick to a particular address, right? Right. And this is that notion of listening for connections, as well as making connections. We actually have to bind a socket to an address. We'll talk about what a socket actually entails. A socket has creates an endpoint, creates a connection between two endpoints. Those two endpoints have, in fact, um, IP address, of course, and a port number. But both sides have an IP address and a port number. So it's very important to note that you need both of these in order to have a connection, right? We'll talk more about that as we go along, but that's part of the conceptual thing. This binding a socket is not just for the client, it's for the server. It's not just for the server, it's for the client as well. So we'll talk more about that. How do we make connections? How do we actually transfer data back and forth? We will have a very simple, we'll start off with a very simple server that just um, gets data and then we make a connection, it sends the time and moves on. Then we'll create one that actually gives us back any data we sent to it, it gives us back and so forth. And then we'll discuss client server operation as well and how that overall process works as well. Sockets, however, we're going to talk about it, are the ultimate form. It's a network-based IPC. The goal is to basically to achieve the same interface for intermachine as intramachine. So we can cross over machine boundaries via network IPC in a similar way that we might cross over local boundaries, right, on the same computer. So sockets are an abstraction of a communication endpoint that allows us to do both of these, right? If you think about an IP address, we have an IP address locally and we have an IP address remotely, right? So we can very easily have the same interface for both using sockets. So a socket descriptor is a handle to a socket. It's very much like a file descriptor. Don't get it complicated. In fact, more of the majority of functions that work with files also work with sockets. So very, very simple. Remember, everything is a file in Unix. So this, of course, makes sense for a C perspective, from a C perspective. So to create a socket, we use the socket function, int socket. It takes a domain, takes a type, and takes a protocol. Protocol is usually set to 0 to select a default. We don't really do much with protocol here. Socket type determines the type of communication mechanism. You're referring to TCP or UDP, right? Sort of. We'll see that in an example. Domain determines the nature of the communication. So let's look at it. Okay. Yep. Not exactly what you think of, right? So the socket domains are actually, are we referring to IP version 6 or IP version 4 or IP version 4 or IP version 6? Everything we're going to do, we're going to stick with INET, which is IP version 6. You also have this weird AF Unix. So if you are communicating on the same machine, you might actually use a lower level socket called AF Unix. It'll actually work exactly like a socket, but It's actually on lower level Unix. We do this for performance reasons, so we don't have to interface to the network card, but it's pretty rare. The network card is actually uses DMA frequently, and as a result of that, it's very, very rapid. The socket type is what you're thinking of. If you want to use a datagram, you use socket datagram. If you want to use socket stream, it's a TCP interface. There's two more. Sock raw gives a datagram interface to IP. It's not UDP. It's you creating a specific protocol right over IP, right? It's a very, very low level thing. This is used frequently in security tooling when you're sending special types of packets and so forth. Socket raw would be the one you'd be kind of interested in. Sequence packets, the same basic premise, right? Fixed length, reliable sequence connection oriented messages, but it is absolutely a lower level version of stream. Okay. Socket stream is your TCP interface. 90% of us, we're thinking about being application developers, are going to focus on dgram and socket stream. Okay. Ta-da. That's just the way it works. We're going to focus on socket stream almost entirely because it doesn't really benefit us that much to do much with the UDP interface. Because we're not going to very complicated servers. As an example. Socket and open are very related. Some important functions in our operations. So close deallocates the socket. Read is equivalent to receive without flags, and write is equivalent to send without flags. Right? And you're like, wait, what? We're going to see an example in a little bit. But socket and open are very, very, very related. You have close and you have a read and write, right? If you want to receive without flags or send without flags, read and write are equivalent. Sockets and bidirectional. Communication via sockets is not like the other ones, right? It's bidirectional. We can actually communicate in both directions. That means I can speak and you can speak. And that bidirectional is bidirectional at the same time. You can have two threads on both sides manipulating read and write input very, very easily. We can disable the IO on a socket with the following. You give it a sock ID and how. The how parameter, you can disable reading, you can disable writing, you can disable both. Why would we do this? Well, close deallocates the endpoint only when the last of active reference is closed, but shutdown allows us to deactivate the socket. You're like, wait, what? So close gets rid of the socket, but shutdown allows us to deactivate or prevent not prevent, but identify that we're done writing, we're done reading, and so forth. Sometimes it's convenient to shut down IO direction to inform the other side that we're done, as an example. We're done reading, we're done writing, whatever. It's a signal that we're done reading. So that's your primary reason for doing this. We don't do this in this class, but you could. All right, we need to talk about byte ordering because life is like that. Byte ordering is the order in which bytes are considered. You have a byte and you have zeros and ones. A byte, of course, is 8 zeros and ones together. Yay, no. Yes, that's correct. I'm sorry. I don't know why I was brain farting on that. But the ordering matters. And so what do you mean? Well, the highest byte address occurs in the least significant byte. You're like, wait, what? It's the order of addressing, right? It just means that we're going to store the numbers in two different ways. And we refer to as big endian. The highest byte address occurs in the least significant byte. Solaris 9 uses this, SunSpark uses this. Little endian, the least significant byte, contains the lowest byte address. Okay? That means the lowest byte address is on the right rather than the left. Pretty simple. The host network, host implies the computer you're on, network refers to the fact that TCP uses big endian. So we refer to network byte ordering, we're referring to big endian, okay? We will almost always have to do this slight comparison or change because that is the way low-level sockets work, okay? Bigger systems would automatically do the conversion for us. That is not the case with this, right? So, bigger systems. I mean, like a network, if you're writing this in C++ or you're writing this in Java or Python or whatever, you would not have to worry about byte ordering. It's only something that's important with very, very low level socketing. sockets such as C. One of the things to remember about this too is we don't actually do anything. We don't really care about this. We just need to know that it exists. Network byte ordering, what that actually means. Now, we have some mechanisms for network byte order translations. HTON, host to network, host to network, network to network, right? And you're like, wait, what? Did I get that wrong? So you get the long and short. You get the 32-bit and you get the 16-bit. We're going to see this back, right? Network. I think that's network to host. We'll talk about this. We'll come back to this because I'm brain farting on this exactly. I know HTONL and HTONS goes to network, and that's the one we need most of the time. HTNONS. But I'm going to look up the just to verify at the end of this presentation. I'll give a 5-minute review of the network to the other ones. We don't use those as much, which is why I'm a little confused. I'm just brain farting. Address format. A set of structs allow us to perform about 90% of what we're going to do. 90% of what we're going to do is we're going to set up these structs. Done. It's actually that simple. Remember, a socket has 2 endpoints, right? Each socket has 2 endpoints. Imagine a tube, and each tube has an endpoint. So we have socket address in, and in address. Let's look at what they actually do. Socket address is actually very simple. It takes an SA family, which is the address family, like think IF, INET, those kind of guys, and it takes 14 bytes of a protocol address. So what does this really look like? Well, it holds the SA family, which is AF, INET, whatever, those things I was telling you about. The A data typically contains the destination and port number for the socket. How do they actually get it in there? It's a character array, right? We're going to see that later. Don't worry about it right now. We're going to see that later. Okay. Socket address in shows the SYN family. We have a port, and they have the in address, the SYN address. Okay. Now, why do we have the SYN 0? SYN 0 is just to size it up so that the SYN address and the socket address in and the socket address are the same size. That is all it's doing. Don't overcomplicate that. Okay. Note the in address here. We're going to talk about that later. Programmers created a parallel structure for socket address, which can be substituted. Socket address in, that's what we're talking about. We have a SYN port and SYN address. Both of these have to be in network byte order. It's actually very simple. We have some calculations to do it. Simple, quick mechanism to perform this is INET address. Takes an in address T, converts an IP address in numbers and dot formation into an unsigned log, which turns it into network byte order. Perfect, right? It's a very simple mechanism for creating that. And it's this INET address function. Port also has to be converted, and that's the HTONS. We don't really have to do much there. And you go, why is the short version? We very rarely need to use the long because port numbers are not larger than a certain size. And so HTONS is almost always perfect enough, right? We don't need to use 32-bit address, right? Network to address converts the address specified in address to a human readable string. So if we need to take this and convert it back to something we need to read, we can very quickly do that. Okay. Ideally, we shouldn't be forced to know the internal structures, right? Additionally, we want to look up perform host name and servers lookup without scanning etc and etc services. So one thing we can do is get host by name, and we can pass a host name, and it resolves the IP address for the given host name, right? It's like a DNS request, okay? But let's see what a host is. So HNAME is the official name of the host, is the full address. The alias is a pointer to a list of aliases, the other addresses it might have, and the address type, the type of address it uses, the length of the address. Don't need to get into much detail. The next one is a pointer to a list of address of the host. Note, you may have more than one address as explained earlier. In older systems, there was only one field, so we have to have a pattern. One thing I want to talk really quickly about this. This is a host name to IP address. So you have a name, and clearly you can have more than one address for each host name. Okay, duh, right? So that's why we need to have this kind of be in our address list. Associating the address with sockets. So what do we want to do? We want to bind the given socket. We created the socket. Now we need to bind it to the given address. Ta-da! Return 0 if okay, -1 on error. Some restrictions. Address specified must be valid for the machine it's running on. You're binding to your address, not some remote address. Address must match the format specified by the address family. So if you're specifying an IP4 address, you better have an IP4 address. If you're specifying an IP version 6 address, you better have an IP6 address, what have you. The port number cannot be less than 1024 without appropriate permissions. You need to be root. So we're going to stick our addresses always in above 1024 range. Port number is 0, gives you the first unused port. I don't recommend this because then you have to identify what the actual port is. You can do it. You may see an example of it just to see how it works. This is a very common one as well. There is a field called inaddress any, which allows you to automatically fill in the IP address of the machine the computer is running on. This is actually really useful for us, so we're going to use this periodically, okay? Or we'll at least see what that looks like. Defaults and discovery. Since we have some default modes, we'll discuss what can we actually figure out what we're bound to. So you can get the socket name, which gives you the address bound to the socket. Get peer name. If the socket is connected, we get the address of the remote peer. Okay. Remember, sockets have 2 ends. Each end has an IP address and a port number. So if I want to know what the address and the port number of my remote party is, get sock name gives me mine, get peer name gives me the remote one. Time to actually connect. If we're dealing with a connection-oriented network, such as sock stream sequence packets, we need to establish a packet. How do we do this? We connect. We give it the socket, give it an address. There may be many reasons for failure. We don't really care. One thing I'm going to talk about later on is you can actually connect with socket datagram. And all that does is it's still sending datagrams across, but what happens is we no longer have to put the, we no longer have to address each packet. We'll talk about that later, okay? Server mechanism. The server announced that it is willing to accept connection requests by calling int listen, okay? This is not the block. What this does is identifies to the operating system that I am listening on the given port, okay? Without this, the operating system does not know you wish to wait. Operating system will not, the TCP system, the substrate that the operating system uses will not translate this to a port number that is open and willing to answer request, okay? We retrieve the connections from the server by calling accept. When we have the accept, this is the block, by the way, accept blocks until it gets to an actual client. The descriptor returns a descriptor connected to the process which called connect. In other words, when we're on the server, we accept this sock address is the descriptor connected to the other side. Okay, not our socket, the other side. So how do we transfer data? So connection ordered, we send and receive. We don't need to do anything, right? It's been open and connected, so we just need to send and receive, right? Write and read. If it's connectionless, we just use the following methods. They're slightly different, called send to and receive from. In send to and receive from, we actually identify where we're going, the source and destination of the packets. Receive from, similar idea. We identify where we're accepting packets from. So let's look at send real quick. Use the socket description, size of bytes, and flags. Identical to write, except you can have some special flags for, sockets such as don't route. This is for situations in which you don't want it to go off the computer or you don't want it to go outside of the broadcast range. I'm trying to think of the word, right? Routing requires you to go from one network to another. If you want it to remain in the same network, you would leave don't route. We don't really use these too often, but you could use them. Receive does the same thing, makes a socket FD, gets a buffer of data, a certain number of bytes, and then we have some flags as well. Received data obviously is data that we are getting. Send to and receive from, same idea as the other ones. If you look at the send, socket FD, buffer size, int, and you have flags, buffer, blah, 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 your flags. The difference is you're also getting a socket address and its destination length. The same thing you would have in the connect, you have here. The same thing in the receive from and the bind, you have here. That's the additions to the send and receive. Now, this is what I was talking about earlier. What benefit do you get by connecting to a datagram network? What do we get? So the packets are still being sent via datagram options, right? Each socket, each packet is being connected or sent across. There is no actual connection. You're not forming a TCP connection over I want to say DHCP, but that's not right. Over a datagram network. That's not what's happening. What's actually happening is all you're doing is allowing yourself to now use send and receive. Okay. What you're doing is you're identifying that I'm going to communicate with this guy. So as a result, all your sends and all your receives are going to go between the two endpoints. That is what a connection gives you. That is it. Okay. You don't have to identify the source and destination of each packet. Socket options we can get and set. They're generic options for all socket types, options to manage at the socket level, but depend on the protocol and protocol specific options. We aren't going to do anything with these, so we're just going to identify that we can set socket options and get them. We're not going to do anything there. But here's some options we can do with accept con, return whether a socket is listening. We can identify that. Broadcast datagrams if value is non-zero. Bypass normal routing. Keep alive. Keep alive is weird because it does it for you. You don't have to do anything. What keep alive does is it sends what we refer to as a keep alive message using the TCP protocol. Internally, we don't have to do anything. But what happens is internally, every so often sends a message saying, hey, I'm still here. That's it. It's referred to as a keep alive message. Sometimes you have two endpoints that aren't communicating for whatever reason. Maybe they're waiting for each other. Maybe they're processing data, whatever. After a period of time, they hang up because they go idle. The keep alive messages are designed to keep them alive, right? Not let the operating system close them. Reuse address. You can't reuse an address if your bind is non-zero. But this is very important in servers where we have large number of processes handling the same request. We actually can reuse that address and say these 5 things are actually listening on this address. And you can change the send sub buffers and the receive buffers. Okay. Again, we don't do that too often. We do very little here. Very, very little. All right. Client server model is used to divide the work of the internet programs essentially into 2 parts. You have the server, which is a passive or what we refer to as a slave. It waits for requests and does the work. One thing I want to mention too, is we want to be very careful about this from a system perspective point of view, is the server is the one with the privileges that can do what you need to do on the server. Sometimes you're not actually creating a server that sends requests and gets back data. You're identifying that the server should do this or do that. You're changing the state of something as an example. If that's what you're doing, then the server has to be the one that does that element of work, right? You don't allow the client to do it as an example. But the server sits around and waits for requests. When the requests come in, we process them and we serve replies. That's why it's called a server. The active client is active. It sends requests, waits for, and receives server replies. Typically, when it's done connecting, it disappears. It no longer needs to remain connected, and we're done. Okay, so let's look at pseudocode. So very thing for the client is we're going to go ahead and get the server's address. We're going to form a working address that can be used to talk over the internet. And we're going to use that address to connect to the server. While we're not done, we're going to wait until there's either information from the server or from the user. If information from the server, parse the information, show to user, maybe update local state, whatever. Else, we've got a user command. We're going to go ahead and parse it. We're going to send it to the server or deal with it locally. Okay, done. As an example. Okay, done. But note, you have to get the server's address. You have to form a working address and you have to connect. Okay. Server pseudocode, you have to bind a port on the server so clients will be able to connect. Then you listen on the port for connection requests. Then you, in a forever loop, you accept incoming connection requests. If this is an authorized client, maybe we don't want to let everybody in. We're going to do some work. Otherwise, we're going to abort the connection. We have the ability of preventing connections from going through, of doing connections. We have the ability to prevent certain connections from doing anything. And so maybe we want to do that. We're going to receive requests from the client. If it's authorized, while the connection is still active, we're going to receive requests from the client. We're going to handle requests. We're going to send results of the request or error messages, and then go back into the while loop. One thing we want to talk about briefly is there's two elements of this that we need to talk about, okay? So from the client perspective, we have to open the connection. We connect, and then we actually have to set up the IO, the send and receive buffers. It's totally doable, not very difficult. We'll see lots of examples when we do it, okay? The same thing's true with the server. We have to set up the two-way connection as well. That's not shown here, but it is very, 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 very vital for good communication on the server. The other thing too, and to remember is this client pseudocode is built from a very specific, what I used to call an echo server. And what the echo server does is it communicates to the server. And anything it sends, anything you type in, it sends it to the server, and the server responds with the same data right back to you. At the same time, it waits for a quit command. If the quit command comes in, it disconnects from the server and quits. The server listens for connections. As the connection occurs, it communicates with the server until the server quits, right? Until the connection is no longer alive. This was specifically done for a very specific server. Now, let's do the same thing. So we'll start with the server. We're going to do the bind, as always. We're going to listen, and then we're going to do a forever loop where we're accepting incoming connections. As soon as the incoming connection goes, we're going to check to see if it's an authorized client. If it's an authorized client, we're just going to send the date and time, right? And then disconnect. Boom, that's our process. So now our client pseudocode, we get the server address, formal working address can be used to talk over the internet. We connect to the server. While we're connected to the server, we don't do this while loop thing. We just get data from the server and assume the server's going to quit. Why? Because that is the organization of the path that I've chosen for my actual interaction between the two applications. We're going to see this a lot, and it's going to be a little confusing. But one thing to remember about our client and server is they are actually going to be two different processes. And as a result of two different processes, it's very important to understand they're doing a tango. And yes, you can get a deadlock just as easily as you had threads, because now we're dealing with two processes that are waiting on each other, right? So it's very important to understand that notion of protocol that I talked about so much, and we're waiting for requests, and we're sending requests, and so forth. We're going to see lots of problems occur, and where and which and how do we deal with those problems? We're going to see lots of those when we come back on 12.3 and 12.5. Those probably incorrect dates. Let me just double check. 12.2 and 12.4. Okay. But the server process is always going to work the same. We're going to bind to a port. We're going to listen. We're going to accept. We're going to connect to IO. Listen for connections. Wait for the data to do something. Wait for data. Get the data. Respond to the data. Right? Yes? In a forever loop. Client connects to the server by getting the server address, doing the things in order to connect to the server, and then connecting IO, do its dance, and then quit. Okay? Pretty much how it works. I wrote this client pseudocode just to give you a feel, but obviously it depends on the application perspective and what it actually looks like in real life. All right, we discussed socket concepts, including IPC. We explained socket creation, including domains, types, protocols, and addresses. We discussed socket functions, including send, receive, close, and IO relation. We didn't really spend any time with IO relation, but we're going to spend a lot of time with it when we do our examples. So Yay. We explained binding sockets to addresses, listening for connections, making connections, and transferring data. The big one we didn't do anything with is transferring data. Okay, we'll talk more about that as we go along. And then we discuss client-server operation using sockets. There's a couple of things we've not really done well, and we'll talk about those now briefly. We'll make sure we know that we're going to talk about them on 12.2 and 12.4, the last week of school. One thing we haven't talked about is when we talk about disconnecting from the server, right? When the server disconnects, what do we do, right? If you've done your communication right, then you know the client's disconnecting and the server's disconnecting, and then bang, all works great. But what happens when there's an error? What happens when the client disconnects and you're expecting it not to disconnect? We'll talk about that as well. We didn't talk about that. We didn't connect IO to this at all as well. When we talk about client server, we have IO, so we're going to wait on IO and we're going to send IO. That is what we're talking about with the receiving request and handling request. We're going to wait for instance, a string of text, or we're going to wait for a new line of text. We'll talk about this in more detail. And then we're going to send a line of request, and that's going to indicate that, hey, it's now your turn. Okay, we'll spend a lot of time with protocol. We'll spend a lot of time with formatting messages. We'll spend a lot of time with IO, and we'll spend a lot of time error correcting. One other thing we're going to talk about briefly, we haven't done this, but by the end of the class, our simple server will also be threaded. We'll also have, I'm trying to think of the word. We'll also have, daemon-like aspects as well. We'll connect the daemon things to it as well. So we'll wrap up with that. But our first iteration of this is a simple server, simple client that just sends socket data to each other and from each other. And then we're going to have one that communicates in more detail, and then we'll look at errors and so forth as we go along. And that is that. I hope you all have a wonderful Thanksgiving vacation. I hope I am as well. Look forward to seeing you all on December 2nd. Y'all have a great day.